So when we think about lone pair electrons, they're taking up more space, and this means that they're going to experience more repulsion in thinking about the lone pair electrons with either other lone pair electrons or with bonding electrons. So let's think a second about the order that this will be in. The biggest repulsion we would feel is if we have two different lone pair electrons or lone pairs. They're going to have the most repulsion. In the middle is if we're talking about a lone pair with a bonding pair. And then the least repulsion is going to be between two bonds or two bonding pairs of electrons. So let's look at an example of where this comes up. So the first example I'm going to talk about is a molecule that has the geometry of a seesaw shape. And once we get to having Professor Drennan actually show you that shape, you will never forget seesaw. That's going to be one of the easy geometries to remember. But the first thing that we need to consider in terms of this shape, which starts if you picture, first of all, and these models sometimes don't quite stay together, we could actually have two different possibilities. The first is the idea that we could have an axial lone pair, and the second is the possibility that we could have an equatorial lone pair. And we could consider both, and we should be able to use our VSEPR principles to think about which one is actually going to happen. So if we think about having an axial lone pair here, that would mean that these lone pair electrons are going to be within 90 degrees of three different lone pairs. And actually, we'll see later, it will be more than 90 because they're actually going to push them down. But in terms of considering how many bonding electron pairs they'll repel strongly, what we care about is anything within 90 degrees initially. So what we would see with the axial lone pair is that we have three lone pairs that we're going to very strongly repel. Now, would you tell me, if we think about an equatorial lone pair, how many different bonding electrons or bonding pairs that will strongly repel if we have an equatorial lone pair? So you might need to look at your notes to actually compare these two before you submit your answer up here. All right, let's take 10 seconds on that. Okay, strong showing with the clicker questions today. It's going to be a tight race for the clicker competition. It's correct that the equatorial is, in fact, has only two that it strongly repels. So actually, it's probably easier to look at Professor Drennan's model here to see that. So it's where the equatorial lone pair is that is the actual seesaw geometry.
So how many of you had seesaws in playgrounds when you were growing up? Oh, a lot of people. I know that they're not considered totally safe anymore, so some of them are going away. So this is seesaw. Now you should never forget it.
All right, so seesaw, we've got seesaw. Just to point out a few more shapes, we took one out. We replaced one bond with a lone pair in terms of seesaw. If we have AX3E2, now we have two equatorial lone pairs. This is called the T shape. T-shaped. See, these aren't too hard to remember the geometries, the geometry names. And we also can think about if we have AX4E2. So now, in order to get our lone pairs as far away from each other as possible, they're going to be on the axial position. And this is called square planar.
So this is easy to remember. Square, also planar.
All right, so let's talk a little bit now about what the actual angles are between bonds when now we have these lone pairs present. And remember, what we said is when we have a lone pair of electrons, they actually are going to have more repulsion than if we just have a CH bond or a bonded pair of electrons. So essentially, what that means is that in molecules that have lone pair electrons, so for example, if we look at NH3 or ammonia versus methane here, and Professor Drennan is showing those models to you here, what you end up seeing is actually that the bonding angle in NH3 between the NH bonds is smaller. And you can't see it with these models because these are not actual lone pairs. But if they were actually repelling each other, they would be pushing those bonds as far away as possible. And instead of being 109.5, you'd see that the angle is now 106.7. So it's a smaller angle between bonds because you have more repulsion from those lone pairs pushing those bonds down.